Alrighty, so we had, remember, what we're really looking at with these, because we're heading to infinity. If it said as x approaches 0 or 2 or 5 or anything else other than infinity, we look at it different, right? But when it says infinity, we're talking in behavior. So we want to know how fast things are growing kind of way out at the infinities. And if it's a rational, and we just have equations on the top and the bottom without sign and, natural log and all that kind of stuff in it, then we're just looking at top heavy, bottom heavy, tied in degree. Here, we're still really looking at top heavy, bottom heavy, right? But it's not as obvious as the exponents. So if it's top heavy and then the numerator is growing faster, then what is the end behavior going to be? If it's top heavy means we don't have an asymptote type of thing, right? So we're going to infinities. If it's bottom heavy, we're approaching 0. Okay, beautiful. And the order in which we rank things was Feppel. What could we say? See, I told you to remember it. It's weird and crazy. It was the first thing somebody blurted out, and we just stuck with it. Factories eat people's legs, and you can remember that. It's a horrible thought. Hope you never work in a factory, but I guess it happens. All right, so given that, and you think about what's happening here. Now, trig functions is not even in there, right? But we can think about what we know. We know what a sine function looks like, right? It's just going up and down and up and down and up and down and up and down, okay? But then x is growing to infinity, so what do you think this limit would be? 0, because as sine is going up and down and up and down, the denominator is getting bigger and bigger and bigger because it's linear, right? Or if it was exponential, this is technically exponential because it would be like x to the first, right? So it's exponential. So the numerator is going to get really, really big, and the denominator is kind of bouncing around, but it's still getting really, really big, and that means we are approaching 0. Okay? We good with that? All right, so e to the x over x. So is this top heavy or bottom heavy? Because factories eat people's legs. This is an exponential. This is did I say exponential again? Dang it. This is a polynomial, not an exponential. It has an exponent. I do know the difference, and I'm sorry if I'm confusing you. This is a polynomial function, right? And it has an exponent, but it's a polynomial. Either way, we knew it was a linear. So it's polynomial in trig. Here, this is exponential because the variable is in the exponent. I know I said it wrong yesterday too, and I apologize. This is a polynomial because it's like x to the first. And exponentials outrank polynomials because eat becomes 4 people, right? So that means that this is top heavy. So what are we heading to? Infinity. Or it could be negative infinity, right? So we got to think. Let's just kind of think about this. This is e to the positive infinity. That's going to be a positive number, right? X to the positive, that's positive over positive, so it's just infinity. Okay. If it was heading to negative infinity, then it would be different. Okay. The sign doesn't fall under any of them because it's a trig function, but since we know what it looks like and we know it's not really growing, it's not growing at all. It's kind of not staying the same, but it's just bouncing between 1 and negative 1, and so that's how we know that. That's why this one is bottom heavy. Yes. Does that make sense? That's why I drew the little graphs. I'm sorry, I should have been more clear on that too. Good question. Are we okay on this one? Because sine does not fall under that. And maybe there are some other things that don't. Probably mainly just the trig ones that you would kind of have to think about a little bit differently. Good question. All right, so let's look at F. What do you think about F? Is it different than E? What's the only difference between F and E? The exponent is x to 100, the 100 power, but this is still an exponential over polynomial. This denominator grows faster than this one, but this numerator still fully outranks that, right? And so that means this is also infinity. So then, x over the natural log of x. This x represents a polynomial. This represents a log. People come before legs. So it means that it's top heavy. And so my answer is infinity. And understanding what the graphs look like can help you with the positive and negative infinity also. Because you're going to infinity like this with y equals x, and you're going to infinity like this, so it's positive over positive, and then you know what it's looking like, okay? Or you can substitute it in. Like sometimes the pictures help a little bit more, whatever makes the most sense to you. All right, so what do you think about H? Top heavy, bottom heavy, tied in degree. Bottom heavy, so what's my limit? 0. Would the limit be 0 if this said the limit as x approaches 5? No, only because it's infinity and we're talking in behavior, right? That's when we think about FEPL, in behavior. Think of it, it's the end of your legs because the factory ate them. Okay? So then I, what do you think about this one? Top heavy, bottom heavy? Top heavy, because this is your factorial, which outranks everything, and this is an exponential, and so it's top heavy, and it would be positive infinity. Everybody okay with that? We good? Okay, good deal. All right, so grab what you have for today. Make sure I know what, 27. This is going on page 27 when we're done. So we're going to use the idea of our limits and what we know about some functions to talk about continuity and discontinuity. The concept of continuity and discontinuity is not brand new. We did look at this in pre-cal, but we didn't talk about it limit-wise. So it's an often misunderstood topic because the English word we use to continue means to keep going, right? So that's what continue means, but continuous, it's like an unbroken line. So if I can put my pencil down at the beginning and draw the entire thing without picking it up, that's what makes it continuous, okay? So a function is I just said this. A function is continuous if you can draw the graph without lifting your pencil, not the fact that it goes on forever. Because maybe it doesn't go on forever and it can still be continuous, like if it stops at x equals 6 or whatever. So we'll use it to build our official definition as we go along, but let's fill in this chart a little bit. We have two major types of discontinuities, and did I scroll too far? No, I didn't. Okay. We have non-removable and removable. Okay. Non-removable and removable. Those are the big categories. And then there's other types. Okay. So when we did this in pre-cal, one of the non-removable types we talked about, we called it infinite. You can call it other things, but that's kind of how it was in our notes in pre-cal. Infinite discontinuity, that implied that we had an asymptote. So we know that if we have an asymptote, there's some discontinuity on our function, right? So it can be asymptotic or it's a discontinuity with an asymptote. It's infinite because at the asymptote it goes to infinity. So just kind of know that those are the same thing, right? The other non-removable kind is jump discontinuity. And then the removable can literally just be called removable because there's only one kind, but we also call it point discontinuity. It's where you actually just like pluck a point off the graph, like a line with a hole in it. It's where your holes are, why you have holes, okay? Ask me a question. No, I'm looking at her. She's going, what's your question? Right, so that's why this is discontinuities. We were talking about continuity, so these are discontinuities, because even with the asymptote, I have to pick up my pencil. That's what makes it a discontinuity. So absolutely, with the jump, I literally jump, I have to pick up my pencil, that's why it's a discontinuity. If I have a hole, I have to pick up my pencil, that's what makes it a discontinuity. So good question. We're all good so far? Okay, so possible equation. Somebody want to give me what an equation could look like for an infinite? Could be literally anything as long as, how do we know if we have a vertical asymptote in an equation? Okay, a binomial on the bottom. So if I have f of x, so if I have like x plus 4 in the denominator, right? Then I'm going to have an asymptote where? X equals -4. And then your numerator could be almost anything. And I say almost. What kind of factor can your numerator not have? X plus 4. Because if it does, then it's going to cancel out and it wouldn't be an asymptote, right? It would still be discontinuity, but it wouldn't be an asymptote. So that we don't make up a quadratic and accidentally have that, we could just put like x minus 3. It literally could be anything as long as x minus 4 is not a factor up there. Okay, you with me on that? All right, so then we're going to draw a graph. The graph doesn't necessarily match this equation. I want to put that out there because we're just going to make up equations and we're just going to make up graphs. So if I have this, we can go ahead and put it at -4, but we don't really know what this looks like, and it's fine. We can just pretend like this is at -4. Doesn't even have to. We can look like that, and then maybe we have a horizontal asymptote too, but do your horizontal asymptotes affect continuity? Think about that. Does that affect continuity? No, it affects end behavior, right? Vertical asymptotes and discontinuity, that affects that middle behavior, right? It's not technically a word, but that's what it is. It's middle behavior. End behaviors are horizontal asymptotes. All this other stuff is more that middle behavior there. So, but we probably, sometimes you have one, sometimes you don't, but we can just kind of draw this in. It's fine, whatever. That one technically would have a 0 at 3, but again, we're not trying to really match them up. But I have a discontinuity because as I start to draw, I can do this. We'll have to pick up my pencil to start back over there. There's your asymptotic discontinuities. Okay, we good? Awesome. All right, so then jump. Any ideas what those equations might look like? If the answer is no, that's okay. All right, so jump discontinuity might look like f of x equals, it's usually going to be a piecewise function because you have two different pieces and that's why you're jumping, okay? So let's just do something easy like x minus, let's just use this x minus 3 and x plus 4 again. Totally different graph, and those are two little linear equations, right? But then with a piecewise, you have to have a little domain out there. So we can say that it's x minus 3 when x is greater than or equal to 0. And x plus 4 when x is less than 0. And then I made it super simple, so I think on this one we'll try and actually graph this real line because it'll be pretty simple. So we know that this is the first one, x minus 3. That's just a linear equation that has a y-intercept of what? -3, right? And that's what we get when x is greater than or equal to 0. So that means at -3, and we don't have to put hash marks or anything, but I actually have a point, right? It's closed. And it goes like this, right? Because x is greater than or equal to 0. Then I have x plus 4 when x is less than 0. So I have a y-intercept of 4, but since it's not less than or equal to, I have an open circle. And then it looks like that. Okay? So there's your jump discontinuity. I'm rocking along on this linear, and then I literally jump down here and start back over. Okay? It's not jumping over a hole like jumping over a puddle, because that's different. We good? Every single piecewise function will not be discontinuous. Okay? Because it's possible that you could have like part of a parabola and it's an open circle, and then you have a linear that starts here with a closed circle, and it looks like that. Like, so they still could be continuous even if they're piecewise. So don't think that those things go hand in hand. Jump! Yeah, I don't know. This board, the whole thing went away. Are you kidding me? Y'all, I swear. If I tried to do that again, no clue what just happened. None at all. I'm not even sure I want to know. Okay, not even the first weird thing it's done today. Yeah. Smiley face. It was smiling at me. It was mocking me is what it was doing. Okay, so point discontinuity. We have a couple of different ways these could look. What's one way we know we get a hole in the graph? When it cancels out, right? So let's just kind of stay with this stuff here. So let's say that here we have f of x is equal to, and I'll make this. So I'm going to make that denominator x plus 4 again, and I'm going to make the numerator x minus 3 times x plus 4. So just changing this one that much, I no longer have an asymptote. I now have a hole when x is negative 4. Okay? Does that make sense? And so when x is negative 4, so let's just think about this. If I cancel this out, so I'm not going to literally do that right now. If I cancel this out, negative 4 goes in here, I get negative 7. Okay? So I'm going to have a hole at negative 4, negative 7. We can pretend like it's right there. And then really, after I cancel these out, then I'm just graphing this with that hole. My y-intercept is like at negative 3, so this would just be a line with a hole in it, like that. So here's why people get this mixed up with jump. So if I am rocking along here, I'm jumping over my hole. Don't think about jumping over your hole. It's not like a puddle. You have to literally jump from piece to piece. Here, this is one point that just got taken out, and that's the difference. Okay? Are we okay with all that? All right, so those are our discontinuities. So I want you to look at this right here for our example 1. And so we have f of x, and here's something that we're going to start practicing doing because it matters like a lot. This, we haven't even talked about derivatives yet. Y'all don't even really know what that is. But most of the time, after we start talking about them, if the question's talking about f, your function is not of f. It's of something else, okay? So we want to get used to labeling our graphs. It tells me that the graph is f of x, so we're going to label this graph f. I don't even have to put f of x, but this is f and not f prime. I know you don't know what that is yet, but there's a reason, and we're just going to start practicing now, okay? If it's already labeled, that's great, but sometimes we relabel it anyway. All right, so then we're going to determine all the x values where f of x is not continuous and classify each as removable or non-removable, okay? So you go ahead and think about those. You can talk at your table. I'm not going to make you get up yet. Oh, and I need to figure out I don't even know what time we get out of here. This is 5th period, 12:15. Okay, what you're looking for is the x value where it is discontinuous. So you can say it's removable at x equals whatever, non-removable at whatever. X equals, yeah. Good question. Yes. And you can say like removable at x equals what and x equals what, or like however you want to write it, it's fine. Would you agree that there is how many? 4. All right, so I highlighted the x values where I have discontinuities, right? So, and it says removable and non-removable. So I will just classify them. Get a pen back again. I will just classify them as removable. Let's say removable at and non-removable at. And if you wrote them out each separate, totally fine, as long as they're labeled. At, okay, so let's go from left to right. This right here, is this removable? No. It's non-removable. Technically, it's what? Jump. But this just said removable and non-removable, so that's not removable. We can say at x equals what? -1, okay? And then here, at x equals 1, removable or non-removable? Non-removable at x equals 1. Technically, we call it what? asymptotes or infinite, or asymptotic is another fancy way to say it. It's the same thing. Asymptotic, yes. It's an asymptote, so it is asymptotic discontinuity. It's just a different form of the word. It makes you sound way smarter than infinite, right? Okay, what about at x equals 3? Removable. And at x equals, is that 5? And that's removable. And both of those are what kind? They're removable. What's another word for it? Point. Now look at the difference here. This one has a hole, but there is a value. So when x equals 3, y equals -1, right? When x equals 5, the function is undefined. But both of them are considered point discontinuity or removable. We removed it, we put it back here, we removed it, and we don't know where it went. Okay? We good with that? Yes, sir. This? That's a good question. And the answer is no, because it belongs here, and we actually removed it from here and put it here. And so when we go here, we have to pick up our pencil. The reason we're picking up our pencil to come down here is because there's a hole there. Does that make sense? That's a very good question. Anything else? Okay, beautiful. All right, so on the back here, I was going to make you get up and go to the boards, but we only have 10 minutes left. So I want you to work on example 2. You can do it at your table. And from what you know and from what you can do, see if you can find all of the x values where g of x is not continuous. You can talk amongst yourselves as you work, whatever works for you. I guess. No. I mean, well, I guess no, because I want to talk about some other things before we get there. I'm going to give you another minute, then we'll talk about it. Did you all factor them? Yes? Okay, so I'm going to go ahead and factor mine while you're talking still, and then we'll talk. Let's see, I get x plus 8, x minus 5, x minus 5 times x plus 2. Okay, so let's talk. We've got, you factor, you get this much, right? So because I can cancel these out, that means I have a what where? A hole or a point discontinuity at x equals 5. Okay, even though I have a hole, and that is fine, we talk about it, I know I use those words too, and that helps us understand the graph. And the fact that you said hole was totally fine because that's what it is. But when you were naming your discontinuities, it is a point discontinuity. Does that make sense? So I have a let's see, we can say removable. We're just going to put both of the words just because we can. Removable point discontinuity and then I can abbreviate that. Discontinuity at x equals 5, right? More specifically, just so we understand what's happening here, the ordered pair where that point is 5, comma what? 13 over 7. Because once I cancel this out, I take that 5, I substitute it in here, I get 13. I substitute it in here, I get 7. So the ordered pair itself is 13 over 7. The only thing this question is really asking right now is x equals 5, but there's a reason I want you to have that too, okay? All right, is that the only discontinuity we have? No. We also have what? Asymptote. So we have non-removable, removable, which is asymptote is fine. At x equals what? -2. Okay. We okay with that? What questions you got about that? Now, I'm going to ask you, we're going to write down a couple other things here. For this function, the limit as x approaches 5 of g of x, what is that limit? It's what? 13 over 7, right? Because if I substitute in 5 to the original one, I'm going to get 0 over 0. That's bad, right? I get that because there's a hole there. But whatever this graph looks like, as I approach, there's this, there's the hole, and that's where that is right there. So as I'm approaching from either side, my function value is approaching that 13 over 7. Does that make sense to you? Okay, so then what about the limit as x approaches -2 of g of x? Because I can't do direct substitution there either, right? But do you remember what we did the other day? We looked at it from the left and from the right. So visually, if you think about the fact that, okay, I have an asymptote at -2. I have no idea what my graph looks like, right? But I have an asymptote here at -2. If I'm approaching from the left, I'm approaching from like -2.1, right? And if I put -2.1 right here over and put -2.1 right here, what signs do I get? I get positive over negative, right? So from the left, it's approaching -infinity. It has to look like this, right? From the right, if I put 2.1, that would give me positive, positive, which means it looks like this. So since they are different, what's my answer? D and E, which means I don't need my equal sign. It does not exist. Is it possible? So what if I had said this is my asymptote and this happens? Then what would my answer be? Infinity. So if they're the same, which is possible, right? If they're the same, then it is whatever it is. But since they're opposite, it does not exist. Okay, and we had to look from the left and right. We good with that? Okay, we will start here tomorrow. Good job.